Oh, I know. Oh, I know.
Rotating machine. We start with DC. We have a three type of machine. I'm going to talk about that. Before starting, in one of the homework we uploaded the first homework due next Tuesday. In one of the problems we mentioned cast iron. I think the one is like a donut, something like that. Cast iron, if you go check your book, the DSL for the cast iron is in your book, you know. Maybe later on, tonight if I get time, I'm going to go home 10:30 p.m. tonight. I'm not sure I'll get time to send it down or not. But if I can, I'll send that, I'll take a picture of that page and I'll ask the Concrete to upload it in the class website so it's more good when they don't have the book and at least they will have the graph. But it is one of the figures in your book. I'm not sure, I cannot remember which one is it, but it's one of the figures in the book. Cast iron. I want you to go through one example which the material is not linear and you have to use the BH curve. That was the main intention for that problem. I'll send you the second homework either during this weekend or before this weekend. Will be due the Tuesday after. Will be the Tuesday after. And I'll try to give you the third homework very soon also, you know, because I'm leaving. And will be, I don't know, due to what, I don't know, because I want to upload the solution, you know, as soon as possible. If you put it due the Tuesday after the next, so basically it's going to be 2 days before the midterm this time, you know. If you guys are okay with that, we can bring it a little bit ahead, maybe Friday. I'll give you the homework 10 days before the deadline. But if you can bring it a little bit ahead, it would be great because I can upload the solution a little bit sooner for you if you want to read them for the exam. Any questions? So we're going to talk about the DC machines. Sorry, it is about the electric machine. Is there anyone in this class that still is in the waiting list? So have you talked to Vanessa?
I did today.
What did she say?
She said she doesn't have any control of that. She doesn't have any power of that.
To do what?
To add us to the window.
I told her to open up the waiting list, you know. Why she doesn't have?
So there are sections open, but on Monday, Wednesday morning, some of us have conflicts because we're taking DC 102, which is 9 a.m. So it conflicts with the last section. And one of the Wednesday night sections are closed.
Oh, so she cannot add to those classes. Okay. So this is an internal problem. You have to solely can find some replacement, you know, inside the class to switch your.
Posted on Piazza, but no response. I posted on Piazza, no response.
I saw that one actually, yeah. Sorry. No, you have to guys. So basically, I'll talk to her. If she can open it up still, I'll tell her to open it. But I'm not sure she will be able to. So we have in general, we have a DC machine and AC machine. AC machine, they have many different type of AC machines. We will go to, in this course, we'll go over the DC machine, how do they work, the DC motor, DC generator. Now, when I'm teaching power electronics to next quarter, I'm going to talk a little bit about the control of this machine. In this course, we don't talk about the control. But when we get to the power electronics too, as soon as I cover the main part, I will talk about the control of DC machine because they're pretty simple with power electronics with a DC to DC converter, and we'll talk about those. Then the AC machine, there are three major ones. There's the induction one. Inductions, there are two types. Induction machines, there are two types. They are the bone roller and squirrel. I'm not sure. Can you help me with my squirrel case? Can you like this?
Yeah. EL. EL.
EL here?
Yeah.
Oh, not bad. You know, so a squirrel cage, you know, the reason they call it a squirrel cage, because if you look at the rotor is the moving part of this machine. If you look at it, there is a piece of iron, but it's exactly like this. There is the bars, there is the copper bars like this. They call it a squirrel cage. You don't have any access to the rotor. You're all, here is this windings here, they are shorted here. They call it a squirrel cage. The wound rotor is like this. You have one side, for example, if you are going to draw this one. So you have these windings here. One side they are shorted here. Well, we'll get it 3 wires out. The windings in the rotor, they are like a 3-phase system, Y connected. Usually one side is connected, or maybe not. Sometimes they give you both sides. You know, you can connect it as a delta. But usually it's like that. One side is connected together, it's shorted here, and they give us another 3 wires. They call it wound rotor because the rotor is not like here copper bar. It's a winding. It's put inside the machine. And the third one is a synchronous machine. We'll talk about this one also. Synchronous machine. We'll talk about mostly about synchronous generator. Here we talk about the induction motors because if you look at the induction machine, they are used mostly as a motor. Synchronous machine, they are mostly used as a generator. I'm not going to go too very much into this one because synchronous machine, they have a huge category of the machine. They have a permanent magnet machine, they have a switch license machine, they have the cylindrical machine, they have a salient pole machine. We only go through the cylindrical and salient pole machine maybe, even though I'm not sure what salient pole, you know, we'll get a time to go over it. But we will go through the characterization of this machine, how do they behave, how we can use them for generator and those kind of things. You will learn the basic, at least of the cylindrical machine. If you need to learn about the salient pole or permanent magnet, it's kind of very good base here. If you learn this one, to learn those ones, they are not very difficult. You can go through it yourself. I don't think we will have time to go through those things, you know, but we'll push it as much as we can. So today we are going to start with the DC machine. So let's see how DC machines work. Before we get to the DC machine, I'm going to go review a few laws of physics. You know, I'm not sure, did you read it in the high school or you had it in the maybe physics, you know, when you came to university? I'm not sure. When I was a student, we had this thing in the physics of the second year or third year of high school. We had all these things in that class. Let's see what are these rules we are going to go. Oh, sorry. And before, one more thing, before going ahead, if you look at electrical machines, let's put it in the box. Electrical machine, on one side, we have an electrical energy, and on one side, we have a mechanical energy. Mechanical energy on one side is torque and speed. Here, we have a voltage and current. If you are going this way, we are converting electrical energy to the mechanical energy. What is that? It's a motor, right? If we are converting mechanical energy to electrical energy, it's a generator, right? So if for those ones they had a power system, we have a third type of electric machine. We call it transformer. Transformer also is an electric machine. But transformer, if you remember that, it was EI, let's say EI, E1, I1, E2, I2. It was converting the electrical energy to electrical energy, but it does change the level of current and voltage. It's not mechanical to electrical. It's electrical to electrical. But motor and generators, one side is the mechanical energy, one side is the electrical energy. Now, one more thing, one more basic thing you want to know about the motor and generator, which we mentioned that one, I think, last either Tuesday or I don't know exactly when. If you look at the generator, if this is a generator, let's consider the direction for rotation here. Let's say this machine is rotating this way, right? In generators, mechanical power, mechanical torque, it rotates the machine, right? If we have a hydro in the power plant, you know, the water is coming, right? It's going to turn the turbine. The turbine turns, it's going to turn the rotor of the machine, and it's going to generate the electricity. We'll explain how. So basically, the direction of the speed is in the same direction of the torque, mechanical torque. For every system, there is one prime mover and there is one like a load, is a TE, right? So if you want to write the differential equation of this system, you said Tm minus Te over D, right? This is the, what do you call it, angular, not velocity, angular acceleration. This is the angular acceleration. In Newton, we said sigma f, Newton law, says sigma f is equal to ma, right? These two rules, they are the same. This is for linear system, and this is for rotational system, right? If it's a motor, so again, if a machine is rotating in this direction, electrical torque is going to rotate the machine, and the mechanical torque is against the rotation of the machine. So basically, if you want to write a differential equation for this one, you say Te minus Tm is equal to J, and J is the moment of inertia of the rotor. There is a moment of inertia for it. In this course, usually we don't go through the transient and those kind of things. But as soon as we get to the control of electric machinery and those kind of things, there is a transient. For example, the machine is rotating at 100 RPM. You want to change the speed to, for example, 500. Basically, this handle is going to go up to get to 500. During this time, the speed is going up. There is a d omega over dt, right? It's not zero. And this one is very good. They call it, usually, they call this part of power electronics and control, they call it motor derived. You know, control of electric machines is called motor derived. You know, it's a very extensive course. I'm thinking maybe next year, you know, I'll talk to the department. I like to offer a course on that one, mostly very high level, you know, for those that are interested in motor control and those kind of things. But I think it's a useful course, you know, for those that they want to work in the electric car industry, they want to work on the industry with the drives. They're everywhere there are drives, you know, if you look at it. I'm thinking about maybe next year I'll offer that course, you know, but the department should ask me that. Right now we have 5 courses already and in the power, and I'm not sure if we're going to get any more. So basic of the electric machinery. We have a DC machine, we have the AC machine. The electric machine, they are electrical to mechanical or mechanical to electrical converter. And the 2 types, the 3 types we are gonna investigate in this course. We go through the DC machine, induction machine. There are 2 types. We'll go mention both of them. And we have a synchronous machine, which they have several type of different synchronous machine. We definitely will go through the cylindrical machine to go through the equation. Now, we want to know how basic, very basic, forget all this kind of thing. You know, these are a little bit advanced for now. We want to know what's the basic rule of generator, based on what rules they want. And what is the basic rule for the motor? Just I want to figure out these 2. You know, you guys already know it. Maybe I'll put it on the board. I'm sure you guys have seen this one before. But these 2 rules, I'm going to talk about it. They are the basic of generators and the motor. if you look at every generator, every motor, if you look at it, there should be two magnetic fields. It could be the natural permanent magnets, or could be electrical permanent magnet. What I'm saying, electrical magnet, for example, you have a core and you put a winding here, right? As soon as you pass the current through this one becomes a magnet, right? It's going to generate the magnetic field. So you have to have two magnets in every electric machine. That one is going to result in the movement of the rotor. Just think about it, very simple. Let's say we have a rail here. We have a rail here, and I put a simple magnet here, and S, right? Let's put another, and this rail is such that this magnet cannot slide out, has to stay between these two rails, okay? Let's put another magnet here. Put N here and S here. Put the magnet here. Now, what is going to happen? If I start to move this one this way, what is going to happen? And let's say there is no friction here, nothing here, right? So as soon as I push this one this way, this one is going to start to move from this one, right? If I go very fast, I may hit this one, right? But let's say when I'm hitting it, I'm not creating any force to move it. Yeah, I'm going to come here very fast here, right? So this one, maybe it starts a little bit late, but it's going to still move, right? You know, it's going to start to move late. Now, this is a concept of synchronous machine. Think about it. If you guys, we can start to move this one with some speed. I'm not sure, slow or fast. To bring this one to this close to this magnet, and both of them they start to move it together. You know what I'm saying? When you move this one, that one also is going to move. You know, don't go very fast or slow to create a kind of problem. So these two magnets, if they start to move to the same speed, they call it synchronous machine. Synchronous means you have two magnets. See, this is as simple as this. You have two magnets. They are moving or rotating. This is a linear system. When you get to the electric machine, they are rotating. Two magnetic fields. They are moving with the same speed. They call it synchronous. The synchronous word has come from there. They are moving with the same speed. They call it synchronous speed. So, for either generator or the motors, we have to have two magnets. Now, let's go back to the basic of the generator. Let's say we have a magnetic field. I'm going to put a cross here. This is a B. Basically, I have a magnetic field here. I don't know. It was a big magnet or it was an electrical magnet. The flux, the B is going to the board, right? Cross means going to the board, right? Now I have a conductor. I have a conductor here. This is my conductor. Let's say the length of this conductor is L, right? So think about the generator. What is the generator? Generator, we said the shaft is rotated by the mechanical input, right? Now I'm going to hold this bar myself. This is the rotor. This is the part is moving. I'm going to start to move this one. What's going to happen? If I start to move this one, what's going to happen? Current? Let's say this one is connected. So then they're back here. Let's say this one is connected to a resistor here. R. Very simple. I put a very simple circuit. This switch is open, right? Yes, we can have a current if this circuit is closed, right? But if the circuit is not closed, what is going to happen? We have a conductor with a length of L. I'm moving this conductor with a speed of V, right? That's a velocity, linear velocity. I'm moving this conductor with a speed of V, right? In a magnetic field of B, right? In general, E, we are going to generate, let me see here. So if this is to find out the polarity of the